Okay, today we are going to start looking at, or look at section 5.3, which is conditional probability and independence. We started looking at probability with two-way tables last class, so we're going to do some more of that today with our two-way table stuff. So first I want to start just with some basic probability. So if we think about some things, just general probability, if you have a spinner has 8 equal size sections, each section is numbered a unique number from 1 to 8. So you have 3 questions there. Take a second, pause the video, see if you can answer those 3 questions and see what the probability is. So for example, part A, what is the probability of getting an even number on 1 through 8? Well, 1 through 8, half of them are even, so 1/2. The probability of getting a prime number, in case you have forgotten what a prime number is, that means a number that is divisible only by itself and 1. So prime numbers in 1 through 8 would be 1, 2, 3, 5, and 7. So there's 5 of them, so 5 out of 8. C, what is the probability of getting a multiple of 3? So in a multiple of 3, there's a 3 and a 6, so that would be 6 out of 8. Oh wait, oh yeah, a multiple of 3. So 1/4. There's only 2 of them, not 6 out of 8. 3 and 6, 2 out of 8, so 1/4. Then we have mixed probability, where we make things a little bit more difficult. So we assume we have a spinner that has 8 equal size sections, and each section is numbered a unique number from 1 to 8. So what is the probability of getting 2 even spins in a row? So 2 even spins in a row, well, even would be 1/2 and then 1/2 again. So if you multiplied them together, 1/2 times 1/2 to get 1/4. Again, maybe take a minute to see if you can get these and then see what the answers are. Part B, what is the probability of getting a prime number or an odd number? So when we looked at our prime number, we had 5 out of 8. Our odd number, we had a half of them. So I'm sorry, and so when we put it together, they have to be one or the other, so prime or odd. So all of our primes wouldn't have any odds that weren't prime. What is the probability of getting a multiple of 3 or an even spin? So our multiple of 3 was 2 out of 8, but then we have to add in any other even numbers, so you would get 5 out of 8. So if you have questions on those are just some simple probability things that you would have learned in the past. What we're going to deal with today is what is called conditional probability. So when we're trying to find probability that one event will happen under the condition that some other event is already known to occur is our conditional probability. So you're going to be given something happened. What's the probability of this happening with that known? So when we look at our conditional probability, our notation, suppose we know that event A has happened. The probability that event B happens given is the word that we're going to be looking for conditional probability. That event A has happened is denoted by this. So this is red, the probability of B given A. So that straight up and down line represents the word given. So what's probably that B happens given we know A happened already. So we're going to look at this with two-way tables first. So when we look at this, we have grade distribution. So for example, we're going to let event E be the EPS course and grade L be a grade lower than a B. Notice we also have liberal arts course, we have engineering and our physical science, which is our EPS, health and human sciences, and if you get an A, B, or below a B. So if I want the probability of L, so this would be what we were looking at, for example, last class, finding the probability of L, so finding the probability that you get a grade lower than a B. So if we look at this, one thing you'll notice is there's no totals in our table right here, so you're going to have to total them up. So if you total them up and you have them, I'm going to be honest, don't remember if I have them in your notes or not. If not, write in your totals so that you know. So then if we want the probability of L, which is a grade lower than a B, you can see right here that 3,656 out of our 10,000. So 3,656 out of 10,000. Remember, reduce it to your lowest fraction, or you can make it a decimal. I did not make these decimals. I just kept them as fractions in simplest form. That's what we looked at last time. The new thing that we're going to look at, the second one here, find the probability of E given L. So given that our grade is below a B, So when we're given that our grade is below a B, now all I care about is this information right here where it's below a B. Nothing else matters but that. So given that it's below a B, we want to find the probability that they're engineering and physical science. So here, 800 now out of 3656, our total changes because we only care about the below a B ones. So that's going to change when we're given different information. So let me erase this here. So our next one, if I want to find probability of L given E, now I'm given the engineering and physical science. So now all I care about is this row. And I want the probability of L, so it's a below a B, so now I would have 800 out of 1600. So 1/2 when we reduce that one. So when you're given something, you no longer care about any of the other information except for that part that's given to you in a two-way table. Along with two-way tables, we can look at this just calculating conditional probability on its own with a formula. So when we're calculating conditional probability, so probability of A given B, here's our formula. Probability of A given B is the probability of A and B over the probability of B. Our other notation, just because we learned two different notations, okay, and then again in words, the probability that both events occur give over the probability that the given event occurs. Okay, so notice what's on bottom that we're dividing by is always going to be what the given event is. The choice of which event you use for A and B is arbitrary, so it doesn't really matter. So it also would be true this. Just notice the order that you have it in. Whatever is given is what is going to be on the bottom of our fraction when we're doing conditional probabilities. Okay, so if we look at a couple examples, back to our one that we had in our first section, a survey of all residents in a large apartment complex reveals we had our 68% Facebook, 28% Instagram, 25% both. We select a resident at random. Given the person uses Facebook, we want the probability that he or she uses Instagram. Okay, so we want the probability that we use Instagram given right here our Facebook. So if you think about our I and F, this is just our notation. So that means if we use our formula, we want the probability of Instagram and Facebook just over the probability of Facebook. So Instagram and Facebook would be our 25%. Facebook would just be our 68%. So we're going to have 0.25 divided by 0.68. We get 0.368. So we can use our formula. It's something that you'll need to know. So that's just looking at some given information. What if you're given a Venn diagram and ask for some information? So here I'm looking for the probability that a randomly selected resident reads USA Today, also reads the New York Times. Okay, so we have all of our information from our Venn diagram. So what we're looking for here is the probability of B given A. Remember our formula is the probability of A and B over the probability of A. So when we look at this, we have to figure out these two probabilities. So here the probability of A and B is 0.05. That's our middle. The probability of A is 0.4 because the probability of A is everything in this circle. So it's 0.4. So if we plug those into our formula, 0.05, not sure what happened on my equal signs, divided by 0.4, we would get 0.125. So there's a 12.5% chance that a randomly selected resident who reads USA Today also reads the New York Times. So that's using our formula with a Venn diagram. So if we want to talk about conditional probability and knowing if two events are independent, there is formulas for that. So when we look through this one, when we acknowledge that one event has happened does not change the likelihood of another event. So it doesn't matter if the event happens or not, then we say the two events are independent. So to be independent, we have our formula. There's two different ones. It just doesn't matter. What matters is the order. So first, the probability of A given B is the same as the probability of A, or the probability of B given A is the same as B. So it's always the same. This first probability is always the same. It doesn't matter that it's given or not. We would have the same probability. So if we look at a couple examples, we'll start with some two-way tables. I just put the formulas again up on top right here. I want to know, are the events homeowner and high school grad independent? So I'm going to let the event A be homeowner and B be a high school grad. Okay, so in that case then, what I need to find the probability of homeowner given a high school grad. So I'm finding the probability of A given B. So the probability of A given B on here, so I'm given B, I'm given they're a high school grad, so all I care about is this row right here. And then I want the probability that they're a homeowner, so that would be 221 out of 310. As a decimal would be 0.7129. When you're doing independent, sometimes decimals are easier to use. So for the next thing we have to find is the probability of just A, because I need, if I had A given B, now I need the probability of A. So the probability of a homeowner, so now we're looking at all of it. A homeowner would be 340 out of 500, which is 0.68. And then we compare these two. So to be independent, according to our formula, they have to be equal. So in this case, since those two are not equal, the two events are not independent. So then what I'm going to ask you to do is you're going to be given some information here. Are these events? I'm given whether you're a junior or senior, and whether you earn an A in AP Stats or you earn an A in AP Calc. And then we're going to look at it. And so what we want to know on here for the first one is, are they independent? Are the events junior and AP Calc independent? So given the formula and the information, using the example we just did, pause the video, look at it, see if junior and AP Calc are independent. Also look at the one below it, senior and AP Stats, and see if they are independent using our formula, and then come back, start the video again, and check your work. So for junior and AP Calc, it doesn't matter which event you let be what. I'm going to do junior and AP Calc. So junior and AP Calc would be 7 out of 16. I need to know if that's the same as the probability of junior. The probability of being a junior is 12 out of 33. Okay, if you change those to decimals, you can see that they are not the same. They're not equal, so the events are not independent. Make sure you understand where the probabilities are coming from, and let me know if you have questions. Senior and AP Stats, again, I did probability of senior given AP Stats, which was 12 out of 17, and then that had to match the probability of senior, which is 21 out of 33. Again, they are not equal, so therefore those are not going to be independent. So that is if you will be asked if two events are independent, and you have to give me proof if they are or not. So then we have what is called a general multiplication rule that we can use. So there's the probability that events A and B both occur can be found using the general multiplication rule. So our general multiplication rule is this: the probability of A and B equals probability of A times the probability of B given A. So the probability of B given A is our conditional probability that event B occurs given that event A has already occurred. Just think about what our conditional probability was right there that we looked at. So we're going to use this general multiplication rule to find some information also. So if I look at an example, the general multiplication rule, we have about 55% of high school students participate in a school athletic team. Roughly 6% of those athletes go to play on a college team in the NCAA. So we want to know what percent of high school students play a sport in high school and go on to play on their NCAA team. So we want the and. So if we think about our general multiplication rule, we want high school sport and NCAA team. So from that formula I just gave you, that means I need the probability of a high school sport times the probability of an NCAA team given a high school sport. So the probability of a high school sport, that was right here, that's 55%. And then the probability of the NCAA team given the high school sport was our 6%. So I'm going to multiply those two together to get 0.033. So you can use general information. You would be able to get this out of a tree diagram, or a two-way table. You would be able to find these two probabilities and multiply them together. From a Venn diagram we've looked at, you would be able to find them. Another way that we can find probability using our formulas is with tree diagrams, and we haven't looked at these yet. So a tree diagram shows a sample space of a chance process involving multiple stages. So it would be like tossing a coin 3 or 4 times, something more difficult to look at. The probability of each outcome is shown on the corresponding branch of each tree when we draw it, and all probabilities after the first stage are considered conditional probabilities. Okay, so tree diagrams are best for events that follow each other, events that happen multiple times, like maybe shooting a free throw 5 times in a row, or tossing a coin 4 times in a row. Something like that are logically related that we would look at. So our first example we're going to look at is consider flipping a coin twice. We want to find what is the probability of getting 2 heads. So we kind of looked at this sample space, or we did look at this sample space in class last time. So our sample space would be heads, 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 tails, tails, heads, tails, tails. So the probability of getting 2 heads, we only happens 1 out of our 4 times. So our probability would be 1/4. So something simple, you can list your sample space and look at it. Another way to do this, just so you can see what the tree diagram looks like, would be something where like this. So we are going to toss a coin the first time. I'm either going to get heads or I'm going to get tails, and the probability of each of those happening is 1/2. Then from the first coin, if I toss it the first time right here and I got heads, I toss it the second time, I also either get heads or tails, and that probability is 1/2. Same thing from tails, I could get heads or tails on my second toss, and the probability is 1/2. So then when you want the probability of 2 heads using your tree diagram, the first head right here, and the probability was 1/2. And then to get my second head right here, the probability was 1/2. I multiply them together and I get 1/4. So both those are logical ways to get it, but when we get into more complicated things, the tree diagrams are going to be much more useful for us. For example, recently, Harris Interactive reported 20% of millennials, 25% of Gen Xers, and 21% of baby boomers, 17% of matures read more ebooks than print books. So according to the U.S. Census Bureau, 34% of those 18 and over are millennials, 22% are Gen Xers, 30% are baby boomers, and 14% are matures. So let's suppose we select one U.S. adult at random and record which generation the person is from and whether he or she reads more ebooks or print books. So what we want to do first is we just want to draw a tree diagram of this. So when we're drawing our tree diagram, I was hoping that was going to come a little bit at a time, but it's not. When we're drawing our tree diagram, you're just going to start and you're going to have, let's just say we're randomly going to have our one U.S. adult, right? And from that U.S. adult, there are 4 options. There's a millennial, a Gen Xer, baby boomer, or mature. So from that, we are going to need 4 of our lines going from each of these, for each one of these things. So notice, according to the Census Bureau, we have our 34%, our millennials, which we have right here, all of our 4 things again. So if we look at this and we're just going to say millennials. So we have millennials as one of our options. Well, of millennials, 34% are millennials, so we put a 34 on that one. Our Gen Xers are 22%. 30% are 30% are baby boomers. I'm going to abbreviate in here. And then 14% are our matures. That's what the U.S. Census Bureau told us. So from that, we have information on who is reading books, whether they're reading ebooks or whether they are reading print books. So from our millennials, here we're going to go from ebooks and print books. And from our millennials, 20% read ebooks. So if 20% read ebooks, these have to add to 1. That means 80% read prints. Then we would do the same thing from Gen Xers. We would have our ebook and our print. And so here, 25% are ebooks, which means 75% are prints. And we're going to do that for each one of ours. So at the end, I'm going to give you a much nicer little tree diagram to look at than my writing. So when we look at this, here's what you would have. You have our millennials, our Gen Xers, our baby boomers, our matures, and our probabilities. And then we have whether they read more ebooks or not. So that would be our tree diagram. So the next thing we want to do is from the tree diagram, we want to find the probability that a person reads more ebooks than print books. So we're going to have to put some probabilities together. So here's our tree diagram that we had. So we want to know if they read more ebooks than they do print books. So what we're going to have to do, we're going to take our millennials as 34, 20% of them read more ebooks. So you're going to have your 0.34 times your 0.2 over here. Then your next one is going to be 22% of Gen Xers, so 0.22 and our 0.25. Our baby boomers, 30 and 21, because we're looking at ebooks, so 0.3 and 0.21. And then our last one down here, 0.14 and 0.17. So we're going to multiply all those together, and we're going to get our probabilities of what they equal. And then what you're going to do is add all those probabilities to get your final probability, because we care that they read more ebooks and we care about everybody. So we have to take everybody's into consideration and add them together. So if we do that, you can see here, I'll erase my writing. Maybe I'll erase my writing. Oops. Erase my writing over here. You can see where we were multiplying and adding all of those together. Okay, so you can see we had our 0.34 and our 0.2. We had our 0.22, 0.25. We multiply them all out. We get these four numbers, add them all together, and we get our 0.2098, which is our final probability of everything together. Okay, so our tree diagram helped us out there when we were looking at it. So let's look at part C. Here, suppose the chosen person reads more ebooks than print books. What's the probability that he or she is a millennial? So what I'm looking for here, if I think about it notation-wise, is the probability of millennial given they read more ebooks. So from our formula, that means I need the probability of millennial and reads more ebook divided by the probability of reads more books. So if we look at our information, this 0.2098 is read more ebooks. That's what we just got from our part B. Okay, so millennial and reads more ebooks would just be this part, millennial and more ebooks. That's where the 0.068 came from, is my circled red up there. So then if we work that out, we get 0.3241. So 32.41% is a probability that they are a millennial and read more ebooks. So we're going to use the formulas we used at the beginning along with reading our tree diagram to get some information. We're going to do some more tree diagram examples in class next time. So if you're a little bit confused when we do some in class next time, hopefully that will help you out a little bit. The last thing we need to look at, though, is a special probability rule. And here it's an independent special probability rule. So if we know that A and B are independent, they have to be independent for this to work, we can simplify our general multiplication rule to just the probability of B given A equals the probability of B. Okay, so if that happens, when we want to find a probability of A and B, all we have to do is multiply our probabilities together. Again, only works for independent events, kind of like when we were looking last time and we were looking at mutually exclusive events and we only had a special formula for or. Now we have a special one for and independence. So looking at an example on here, the Space Shuttle Challenger disaster, I get was a long time ago, but you hopefully have heard of that, was determined that the failure of O-ring joints in the shuttle's booster rocket was to blame. So under cold conditions, it was estimated the probability that an O-ring joint would function properly is 0.977. So assuming that the joints succeed or fail independently, so we know they're independent, we want the probability that all 6 would function properly. Will function properly, this is our probability. So for them to function properly, that means that I would have joint 1's okay, and 2, and 3, and 4. Since they're independent, we can multiply all those probabilities together. So probability of joint 1 times 2 times 3 all the way through 6. So I could multiply all those probabilities together right there, and I get 0.87 as our final answer. So if you know they're independent, finding A and B can be a lot easier than what it was when we were looking at tree diagrams and things that were not independent. So we're going to look at some more of this in class next time. You have a short worksheet that just has one question over a two-way table with some different questions on it, and then your sapling for 5-3, and I will answer questions when I return next week. Have a great weekend.